probably going to want to come and get a copy of it so that you can type it, so that you can put it with part 2 and turn it in, because you won't get that back until after you already turned it in, because it needed to compare to what we did in class is what you turned in. Okay? Any questions about any of that? You? All right. I need to show these week 3 announcements. It's one time through, so with these, issue. There you have it. So what did we learn from here? Is this how is this transmitted genetically? Dominant, recessive, sex-linked, autosomal. This disease. X recessive, so sex-linked X recessive. Yes, is that right? Because why? What was a big clue on this? When you look at it, you can tell.
Because it was on the male.
Because only the males are getting it. If you look at that, and it's recessive because
The females are passing it on?
not necessarily. That's why it's X-linked. But it's recessive because a different way. That say the same thing, yeah. There are carriers, right? The females are carriers, therefore the females are passing it on, but that's the key, right? That's what you meant, right? All right, so one of these, again, I just picked a couple of these at random from your homework. So this is dwarfism, okay? In this case, what we want to focus on is the achondroplastic dwarfism. Okay, the achondroplastic dwarfism is the one that we want to look at because it has a autosomal dominant inheritance pattern. All right. Now, having said that, there's a bit of a disclaimer. In 7/8 of the time, it's actually a spontaneous mutation that causes achondroplastic dwarfism. Okay, it's only 1/8 of the time where it's an autosomal dominant inherited disorder. But there's not much to talk about in this class about the spontaneous mutation because this isn't really a genetics class. This is just a brief overview. So we look at that 1/8 of the time where it's autosomal dominant. Okay. So as you would expect, what does achondroplasia mean? What's achondroplasia mean? Without cartilage, right? A without chondrocartilage. And plasia is growth, like we saw before with, the dysplasia and metaplasia and hyperplasia, right? So this is without cartilage growth. And if you look back to your Bio-322 days when you were studying bones, right, you know that you have to have some cartilage before it can ossify and turn into hard bone. Okay? So, achondroplastic dwarfism. If you look at the picture of these guys up here, you're going to see that their heads, these twin boys, their heads are the same size. Their trunks are the same size. The only difference is those long bones, right? The arms and the legs where you're going to need a lot of that cartilage to make the long bones, those are shorter. Okay? There's no deficiencies in mental capacity or anything like that. But as you would expect, the short limbs are going to throw off the physics of the limbs. So you end up with some limb deformities occasionally, not always, but occasionally, okay? There is this primordial dwarfism, that's an autosomal recessive thing. We're not really focusing on that. I don't think that made your list in your homework, but it could have. It's just, again, another example of an autosomal recessive disease. Has anybody ever seen primordial dwarfism? Like on TV or in person?
In person.
No way.
Yeah, I did.
I've never met anybody who's seen somebody in person with that. How, is there a story there, or is it, hey, what's up?
His parents were normal. He was just, it was so long ago, I was younger, but it was so unnormal that I was like, weird.
Huh, okay. I have a picture of that, I think, on another slide here, but again, not a whole lot to say, I guess, at this point about that. Here's your, again, achondroplasia. This is also a good example of the age of the father. You really don't see that very often. Yeah, the age of the mother does tend to make a difference on whether or not, you have any kind of birth defects, birth genetic mutations, that sort of thing. For example, like Down syndrome, right? Does anybody remember like the magic number, or know the magic number on how old a female is before
35.
you start really increasing the odds of Downs?
35.
Yeah, 35, right? So I don't remember the exact number, but if you're like 20, the odds of you having a child with Down syndrome is like 1 in 2,500 or something like that, right? And then that if you were to graph it, it kind of goes very slowly until you hit about 35 and then start shooting up like crazy, right? And that's, I think, why we're seeing a lot more kids with Downs nowadays, just because, there's a lot more change in society where you're seeing a lot more career, as evidenced by you guys, right? And, putting off having children until you're a little older, and then right about the time you hit 35, it starts really dropping or increasing the odds of having a child with Downs. But anyway, that's not what I'm talking about. What I'm talking about here is the other example that you just don't see very often, where it matters how old the father is, okay? In this case, that does cause some new mutations as the father gets older. And I mean older, not, I know you guys think I'm ancient, but like 20 years older than me, kind of older, okay? Then you start seeing that, because again, the sperm's made, I think, millions of them every single day. So there really has to be, you have to kind of be in that old age category before you really start seeing these kind of mutations happening, okay? All right, here's our pedigree-ish thing, cartoon/pedigree of achondroplasia. Really don't have anything to add to that. As you can see, again, just like with our Punnett squares, you have a dominant trait in there somewhere, you're still going to have some odds. In this case, like this is kind of the one that we drew on that very first slide with the Punnett squares, right? You had each parent had a dominant trait, but there was still 1/4 every time they have a child, 1/4 chance or 25% chance that they would have a child that did not have dwarfism. And you can see from this picture that they did actually have a couple of children without dwarfism at all. Did they have any kids that died? Yeah, I really don't know if they did or not. Has anybody ever seen this show?
I went to their farm, actually.
What?
Yeah.
Okay.
We would go and get our pumpkins there. So.
They have a pumpkin farm?
Yeah.
Oh, cool.
They're from
And
Hillsboro, so.
did you happen to ask while you were picking up your pumpkin if any of your children ever died?
No.
Didn't think so.
I didn't.
Don't know. Does anybody happen? I don't know. Okay. Here's a primordial dwarfism again. She's about 6 years old right there, by the way. I think her name's Kennedy. She's about 6 years old in that picture. And she's, I don't know, about this tall, right? At first, when I saw it, and by the way, there's a video link, you could watch it, it's kind of cool. Takes like 20 minutes though, so we're not going to. But if you look at her real close, you can see she has like this overbite. And I thought at first maybe that was part of this syndrome, but if you watch the video, you'll see where they're actually putting her to bed. Again, she's 6 years old, she's that big, but they're putting her to bed like with a binky every night, still. I'm like, well, okay, if you do that to any 6-year-old all the way through until they're 6 and keep them binky, they're gonna have a horrible overbite. So I think that's probably not related to the syndrome. I'm not convinced that guy up in the upper right here either, because for some reason that reminds me of Boba Fett, where he like cloned himself, because that's the exact same face on that dude, just a little version. So I don't know, that might not be primordial dwarf.
So is she mentally delayed?
You know, has anybody ever seen the series with Kennedy?
I've seen it, but I forgot about what happened there.
I never saw the series. Based on that one 20-minute video clip, she kind of looked like she was a little bit mentally delayed, but it was really, you know, again, it was like a 20-minute video clip, so I really couldn't say. It's not like they interviewed her. As far as I know, she doesn't even talk, but, you know, again, it was a video clip, and I have no idea. I can't believe nobody's seen that show. Man, how times change. I'm telling you, just a year ago, everyone was like, yeah, I've seen that show. You know, 2 years ago, like 100% of the people seen the show. But all right, times are changing too fast. Okay. How about this one? Has anyone ever seen polycystic kidney disease? You have? Not outside the body, yeah, but good story.
My dad has it and I have it.
What's that?
My dad has it and I have it.
Oh, you're kidding. So your dad has it and you have it?
And my sister.
And your sister?
I have one sister that didn't get
So this would be transmitted genetically. How? That many people have it? Probably dominant, yes? Again, it's an autosomal dominant, if you notice. It is hitting both sexes, right? So what do you do about that?
blood pressure medicine, diet, ensure diet,
Okay.
diuretic sometimes. My dad's on the transplant list and he's on dialysis.
Your dad's on the transplant list,
Yep,
and he has had dialysis?
he's on dialysis right now.
Okay. Does that mean his kidneys are really, really cystic right now then?
Yes. The kidney function I think is at 17% now.
17%. Ouch. So that's definitely a stage 5 kidney failure out of 5. Well, I'm first sorry to hear that. What about these signs and symptoms? Does that seem pretty
Pretty accurate.
accurate? Okay, why would you get the hypertension, by the way? Not you, anybody else? Why would you get hypertension with polycystic kidneys? Because what?
Because of the small arteries inside your kidneys that control a lot of our blood pressure. You got these cysts pushing on them to increase the pressure.
Okay, yeah, as you can see, if you have that many cysts, it probably is messing with, you know, the filter, the glomerulus, the arterioles, the capillary system, right? And just things aren't getting through like they should be. And of course, what is it, 22 to 25% of our blood that comes out of the heart goes to the kidneys. And yeah, that would make a big difference in blood pressure right there. What would be another danger? This is a kind of a thought. If you had polycystic kidneys, hypertension because of that, what would be another danger of any other organs in the body?
Your heart.
Your heart, right? Because chronic high blood pressure, assuming it wasn't being treated, right? Chronic high blood pressure could lead to what kind of heart issue? that we talked about before, huh? Yeah, hypertrophy, right? Could have a hypertrophic left side of the heart. So it can lead to a lot more issues. Obviously, the rest of that stuff, the back pain, there's kidney infections, that sort of stuff makes sense probably, right? Because I mean, it's a mass. It's a bunch of little masses making a bigger mass, right? And of course, you can kind of expect anytime, again, untreated high blood pressure, we're assuming, right? Could also lead to those aneurysms, whether in brain or
Can it eventually move to different organs, the polycystic
kidneys.
tumors?
As far as I know, it does not. Yeah,
It
it is.
It's interesting because they thought polycystic kidney disease, but the cysts are actually on the liver as well as the pancreas and ovaries and everything.
See, I did not know that.
Supposedly it doesn't affect the function of those organs,
So the cysts go pancreas, ovaries, liver,
everything in there.
but doesn't affect those. Wow. All right, good to know. I did not know that. So, question for you, since you know better than anybody. If your dad gets his transplant, gets new kidneys, is this going to cause future kidneys to become cystic or not?
You know, I don't know the answer.
That's a good question.
That's a good question. I'm not sure, and it doesn't seem like we would consider it because he's not a very good candidate, to receive a transplant. So it doesn't seem like an option for him.
He's not a good candidate?
Candidate.
Oh, well, that's unfortunate. Okay. All right. I'm gonna move on. This is just depressing me. Okay. All right. So obviously these are gross specimens and an MRI of someone with polycystic kidneys. Fairly easy to identify if they get that large, of course.
Wow.
Okay, as you can see, they can get really, really, really big. Okay, sickle cell anemia. Transmitted, autosomal recessive, right? So would you expect to see this a lot or just a little bit in
Well,
society?
In certain areas and certain racial groups. Like African.
Okay, again, as a general rule, you don't see a lot of recessive diseases, except this one does have a unique qualifier where you see it a lot. Okay, especially in certain areas, and that qualifier is what? Why do you see sickle cell anemia a lot more than other recessive diseases or recessive traits? You guys have probably seen this before, right? Bio-222
Yes.
usually goes over sickle cell. So what's the big thing? Why do you see it so often? Yeah. Because like that little thing says in the lower right, it's resistance to malaria, right? So malaria transmitted by mosquitoes can attach to regular, normal red blood cells. Okay? It can't attach to the sickle red blood cells, but the sickle red blood cells, even though they're not as efficient and they do have their issues, they do still carry oxygen, right? So if you have a sickle, or if you have a malaria outbreak, and if you can imagine like this little village in the middle of nowhere with not really a lot of healthcare, a whole lot of people get sick. And the ones without sickle cell anemia, I have a higher chance of dying. They don't make it through the malaria outbreak. On the other hand, those ones with some round blood cells and some sickle cells, yeah, they're gonna get sick, but they're probably gonna live through it, right? So then they live long enough to reproduce, because they're literally the last man and woman standing kind of thing. And, that's why you see this, even though it's an autosomal recessive, you see it a lot more often. Does anybody know anyone with sickle cell? One person here? Wow, two. Usually see a lot more than that. Again, don't tell me any names or anything, but if your person that you know with sickle cell, are they very sick or not sick or somewhere in the middle?
She's really sick, but she gets blood transfusions like I think every month. or
Wow.
something like that, because she has it bad.
Okay. Sorry to hear that. It's like all bad news today, right? What about you? Did you raise your hand?
She gets sick. I know sometimes it's worse than others.
Sometimes worse than others sick?
Like sometimes she's in the hospital.
Oh, sometimes hospital.
Yeah.
Okay. So she has these episodes? Okay. Sickle cell, again, the reason I bring that up is because sickle cell is one of those conditions where it's on a huge, huge spectrum. Okay? Sometimes you have people that are very sick and they're constantly having these crises, you know, where they're having blood issues and possibly blood clots and or, you know, it gets so bad, you know, the anemia that, you know, they have to have blood transfusions and that sort of thing. On the other hand, I've actually seen people who had sickle cell that were on scholarships for the GCU track team. Okay, obviously not affecting them very much, although technically they had it. I have a very good friend who used to be a fighter pilot. He had sickle cell. They grounded him for a while, but then they realized after he fought them that he'd been flying for 10 years already in a fighter jet and it never affected him before. And so they were like, oh, I guess you're okay. And they put him back in the cockpit and he ended up becoming like a wing commander. So yeah, sickle cell is one of those things where it's on a huge spectrum of how severe the disease is. And again, some places you might not even want to call it a disease, right? Because it's actually protective. But you still end up with the autosomal recessive genetic pattern. A lot of times they can treat it by giving on the very last line. Again, normally I said we don't really talk about treatment that much in this class. It's not really the point of it, but sometimes we'll see something like this that the treatment is unusual. So it's probably worth remembering. In this case, hydroxyurea. Okay, hydroxyurea, we give that to somebody and it actually stimulates the growth of fetal hemoglobin. Okay, you guys remember your blood? Where a normal hemoglobin strands are hemoglobin A, you have 2 of those, hemoglobin B, you have 2 of those, right? And that's what's normally in your red blood cells. Okay, in sickle cell, you're having hemoglobin S, or sickle. So it's different, and that's what's kind of twisting and making that odd shape of the red blood cell. So it doesn't change that, but if you give somebody hydroxyurea and it produces fetal hemoglobin, then what was the big thing with fetal hemoglobin? What was the big advantage of it? Yeah, it really, really pulls oxygen to it, right? It has a very high affinity for oxygen. Of course it has to, because that's the only way the fetus is getting oxygen is through that umbilical cord and that blood, where they're stealing the oxygen off from the mother. Okay, so this is one way to help the patient with sickle cell deal with the issues associated with low oxygen. Okay. Not going to do a ton to stop the clotting, as far as, you know, those sickle cells not wanting to go through those small arterioles and capillaries very well. And here's yet another more red blood cells when they first got up there. Because they would be rather hypoxic at first. Good question, though. So move on, yes?
Can I ask a question about that last slide? In the slide previous, it said that the sickle cell trait is one allele for the hemoglobin with the S and one for the hemoglobin with the A. So then when you go about this, like the A and the S, like, is that different than having like a hemoglobin?
Is that different than what?
Like when you see the what do you call it? Punnett, it's not really a Punnett chart, but it's like has all of them. The people with the A and the S, it says aren't affected by it. But that kind of confuses me with the description of it, saying the sickle cell trait is one allele for the hemoglobin S and one for the hemoglobin A. So like go back to.
Okay.
And then like under the causes, the
Yeah.
last one.
Okay, so hemoglobin S instead of hemoglobin A.
Yeah. So.
So I'm here.
Um,
What's the issue?
it was confusing me because it said that the sickle cell trait has one allele for hemoglobin S and one for hemoglobin A. And then it says those who have A and S like don't have the traits.
Oh, so you would think this chart would say hemoglobin B and hemoglobin S is what they had. Is that what you're saying? If they didn't have,
Yeah, like something like that. But I know it's recessive, so I don't know. I just wanted to.
I'm still not completely sure on the question. I'm not completely sure on the question. So you're saying, on the other thing,
Yeah.
you substitute an S for an A. Yes?
Well, it just says the sickle cell trait is one allele for hemoglobin S and one allele for hemoglobin A. So I'm
Yes.
like, okay. And then you go to this chart, and then it has an A and an S, but it's saying that they don't have the trait.
Oh, I see what you're saying. Okay. All right, that's kind of one of those, what I was kind of talking about there's kind of a big spectrum on how bad you have it. Okay, so if you do have the one A, one S, yeah, you have sickle cell trait, and that's probably like my friend the pilot. Okay, he had the trait, but he had enough healthy red blood cells where it didn't matter at all. It really doesn't come out. Okay, you have it technically, but big deal. On the other hand, again, if you took these and ran a Punnett square, you would end up with what they have down here. And some of them are gonna be normal, okay? You got rid of the S and basically bred that right out of that person. On the other hand, when we're talking about the sickle cell anemia, or they call sickle cell disease, that's what these guys were talking about the people that they know that have to go into the hospital, they have to get blood transfusions, they need that hydroxyurea, that sort of thing. So again, it's just, this is a good example of how humans can sometimes add on to a lot from the simple Mendelian genetics, right? There's a lot more to it. And sometimes you have what they call full penetrance or partial penetrance or no penetrance. It really just depends in the case of sickle cell, what your particular genotype is on whether you're gonna really care whether you have it or not. You have it, but if you're like in the category of the AS, you're more like a carrier. So it really doesn't affect you. You just have the trait, they call it. So you can look at it as a carrier.
Are you still protected from malaria if you're a carrier?
Yes, those are the ones that would be more likely to survive
Mm-hmm.
because they do have some sickle cells. They just don't have a lot of them. All right, so, Duchenne's muscular dystrophy, we've seen this kind of before, and that'll make sense in a second. How's it translated? On the X chromosome, that's why there's a big arrow pointing to it, right? Okay, so if you look at this slide, you see the whole thing is a hyperlink. Starts out, you're a genetic counselor seeing a 26-year-old pregnant woman who is referred to your office by her OBGYN. After talking with her, you find that she is particularly interested to know about the risk facing her unborn child with respect to a condition known as Duchenne's muscular dystrophy. She explains that her 8-year-old nephew was recently diagnosed with the condition. That seems like a long time to wait to get diagnosed with it, but the reason it's a hyperlink is because I stole it from Khan Academy, and there it is. That first paragraph is what I just read. It goes on. You explain that DMD is indeed a genetic condition and that it is characterized by mutation in the gene coding for the protein dystrophin. I'm gonna make this a little bigger for you. Okay. Dystrophin is an important structure of protein found in skeletal striated muscle, which connects the cytoskeleton of muscle fiber to the extracellular matrix. Okay, basically, if you look at this, why can't I scroll down? If you look at this picture under here, this is basically what it's saying. Is, you know how you had, back in muscle physiology, you had that actin and myosin fibers, you know, the thin and the thick filaments, and they, you know, they had that little arm that grabbed up and pulled, and that's what causes them to contract. Okay? What you might not have mentioned in that basic anatomy is that my little thumbs here are the dystrophin protein. And those also, while you're doing this, you're connecting to the actual rest of the cell. Okay? So if you think about this, if that other arm, that thumbs, that dystrophin protein is not there, then you can contract your muscle cells all you want, and it's not going to get any traction on the rest of the cell. Therefore, you have these little micro contractions, but it doesn't matter. They're not doing anything, they're not hooked together with the rest of the cell. It's kind of like a slip transmission kind of thing in a car, where it can spin all at once, but if it's not connected, it's not connected. And that's what the problem is with Duchenne muscular dystrophy, is that protein is not there. And what happens instead is you get, after a while of these worthless little contractions, you end up with fat and scar tissue taking their place. So they end up where it looks like they have really big muscles, but in fact it's just a bunch of fat and scar tissue, and the muscles are extremely weak, again because they can't get their traction, and they have major problems with, you know, walking and such. Okay. Again, this, you should probably read this whole thing, but so here's the thing. You're curious if the patient is aware of other family members who have been affected by it. Okay. And here we go again. See that? Does that look familiar? That is the other pedigree chart that I stole and put in your PowerPoint earlier. Right? So, how was that transmitted again? Duchenne muscular dystrophy? X chromosome and recessive, right? Because it does skip generations. X chromosomes tend to hit males only. Have any questions on that? Comments? Okay. All right. So again, here's the more on DMD. You get that very small pedigree up there. Notice that female is carrying it. That's what I was talking about earlier. Sometimes they will put a carrier by shading in only half of the square or circle. That means the same thing as that dot right in the center of the circle. Okay. Disease, of course, is all the way filled in. But as you can see, there are some muscular issues when somebody has DMD. Any questions? Comments? Complaints? Good. All right, so guess what? It's time to do